All right. Recording, life is good. Okay. So, guys and girls. So, hopefully some of these make sense. Now, you guys listen. I'm going to use my choice of words very specifically here, okay? So, where the original has relative extrema, right? Its derivative has x-intercepts, right? Okay, look. Where the original has a point of inflection, the first derivative has relative extrema. So its derivative should have x-intercepts. Do you see it? Yeah. That's where that's coming from, right? Where the original has relative extrema, you guys came up with that pattern, its derivative has x-intercepts. So where the first derivative has relative extrema, its derivative should have x-intercepts. That's going to link my point of inflection on the original to x-intercepts on the second derivative. Does that make sense? Okay, now when I say no pattern here, that just means there's no pattern that works for every function. If it's in this table, that means that it works for every family of function, not just polynomials, not just exponentials, any piecewise, anything. Okay? Any weird function, it doesn't matter. You guys with me? Okay? Now, same idea here. Where my original is increasing, its derivative has positive y values, right? Well, if the first derivative is increasing, its derivative should have positive y values. That's going to link concave up from the original with positive y values on the second derivative. Okay, you guys with me? Okay, second derivative, okay? On your last AP Classroom quiz, I know it's been a few weeks, okay? But you had this word twice differentiable that they saw a lot, right? Twice differentiable. Now, the last time I was here, 2 or 3 weeks ago, just being like a week and a half, okay? We defined this word differentiable. Differentiable means has a derivative. Differentiable has a derivative. So twice differentiable means has a second derivative. Differentiable has a derivative. Twice differentiable has a second derivative. Okay? Lots of you guys are writing these big words, so I'll say it again to give you time. Differentiable has a derivative. Twice differentiable has a second derivative. Sometimes when I explain differentiable, I call it derivativable, even though that's not a word. But it kind of makes sense, right? Derivativable, I'm able to take its derivative, okay? Twice differentiable is twice derivativable. We're doing okay? Okay, so let's practice these ideas just for a second. Let's say I gave you this. This should not go on your ultra lava. This should go in your notes. Okay, I'll give you a second to make the sketch. Okay. Can someone raise their hand and tell me, where does f of x have points of inflection? Can I have someone raise their hand and tell me, where does f of x have points of inflection? Go ahead.
So like it says the x-intercepts, so that'd be like -1/2, 4, and 9, whatever those values are.
You got it. Where my second derivative, right, has x-intercepts, my original has points of inflection. Good. So it'd be x equals -1/2, x equals 4, x equals 9, right? Okay. Now, that should make sense because where my second derivative has positive y values, my original is concave up, right? And where my second derivative has negative y values, my original is concave down. So concave up to concave down, well, definition of point of inflection, where the concavity changes, right? So there was a change right here from concave up to concave down on the original graph, therefore creating a point of inflection. Make sense? Okay? Concave down on the original to concave up on the original, change in concavity, point of inflection. Concave up on the original, concave down on the original, change in concavity, creating a point of inflection. Does that make sense? Okay, good. Questions? Okay, we're going to do some more complicated ones in a minute, but before we get there, we need to talk about non-differentiable situations, okay? By the end of today, I'm going to be able to give you any graph, and you can sketch its derivative, or you can pretend it's the derivative and sketch the original. And it doesn't matter what the graph looks like. It doesn't need to be a nice, smooth polynomial for me to be able to do that, okay? So let me give you a quick one I just want you to try with your neighbors. We're going to do one we haven't done before, okay? So this is the original, and I want you guys to sketch the derivative, okay? An absolute value function. Okay? So take a second with your neighbors and sketch its derivative. This is a little weird one. Be careful.
Down, up, down, up.
I don't see great.
Do you have the black marker?
Yeah.
Check it out.
Okay, what do you think?
It's close enough.
Looks straight to me.
It's good enough.
Yeah, if all else fails, just make the line thicker. Okay. Yeah. I do that sometimes. I just make the dots bigger if it doesn't go through it, you know. Okay, hold on. Remember we talked about how the absolute value is a piece. This is correct. Good job. Okay, we talked about how the absolute value is really a piecewise function in hiding, right? A piecewise function of two linear graphs, right?
Yeah.
Well, the slope of a linear, the whole kind of definition of it is it has a constant slope, right? A linear graph is a constant slope. So its derivative should be the same value over a linear graph, right? Is that fair? Okay. So notice that all of these are negative because they're decreasing. All of these are positive, right? So, sorry, all of these are decreasing, so they're negative. All of these are increasing, so they're positive, right? He did 2 open holes there, creating a jump like that. That's correct, okay? The vertex of an absolute value, even though the absolute value function is continuous, the vertex of the absolute value is non-differentiable, does not have a derivative. Here's why. It has an infinite number of possible tangent lines that can be drawn. There isn't, because it comes to a sharp apex, okay? There's an infinite number of tangent lines that can be drawn. So how do I know which one it is? I don't. It's undefined. Its derivative is there undefined, creating a jump, okay? So we have 4 types. This needs to go on notes and ultra lavas. 4 types of non-differentiable points. Okay? The first one, okay, is anywhere f of x is not continuous. That one, hopefully, is obvious, okay? If my original graph has a vertical asymptote, a jump, or a hole, right? Those are my 3 types of discontinuities, okay? I can't take the derivative of a point that is undefined. Is that fair? I can't take a derivative of a point that's undefined, okay? So anywhere f of x is not continuous, okay? Our second type is infinite tangent possibilities. So that's anywhere that comes to an apex. The most specific, or the most used one, is the absolute value vertex. Okay? So, again, if my graph is differentiable, then I know it's continuous. Okay? Anything not continuous is non-differentiable. However, there are certain types of continuities that still do not have a derivative. And the first one is this infinite tangent possibility. So anytime my graph comes to a sharp apex, there's an infinite number of tangent possibilities, therefore making my derivative undefined. Okay? Our second type of continuous point that does not have a derivative, we've already talked about. Anybody think they remember? Our second type of continuous point that will not have a derivative, we've already talked about. It's already on your ultra lavas. What? Squeeze there, is that what you're saying? No. We've already talked about a time that makes a vertical asymptote on the first derivative. The super straight vertical tangents, like on a cube root graph. Vertical tangents. Vertical? CAL or CLE? Okay. I don't either. Vertical tangents. I'm the worst speller. So that example would be like something like that. That's like a cube root graph. So vertical tangents. Okay, the fourth one is distinct endpoints, like on a square root graph. Endpoints. Here we go. Like on a square root graph, distinct endpoints, okay? Those are our 4 main types of non-differentiability, meaning will not have a derivative. Meaning, when I sketch these graphs, these types of things are either going to have a vertical asymptote, a jump, or a hole in the derivative graph. we've got three types of discontinuities, right? Vertical asymptotes, jumps, and holes, okay? So for all three of these types of non-differentiable points, when I have an f of x graph that contains one of these, right? These four things are going to be making either a vertical asymptote, a jump, or a hole on the first derivative graph. Guys doing good? Any questions? We're going to do a bunch more graph sketching today before we cover our last concept, which is bounces. Bounces, bounces, bounces. Okay. Any questions? Yeah, Chase?
Oh, sorry. I was just making the bounce noise.
Oh, you're making a bounce noise? Wait, do it again. I missed the bounce noise.
No, I don't need to hear it again.
Oh, okay. All right.
It was more like if you heard it the first time.
Yeah. Yeah, just save it for later. I'm sure it was great. All right. How are we doing? Good? Okay, I'm going to give you another graph, and I want you to do two different things. Well, no, let's just do one. I'm going to ask you some questions and give you a sec with your neighbors. What is P of I in this class? Not person of interest. What is it? Point of inflection. Okay, I want you guys to do these four things to this graph. Where does f of x have points of inflection? Where is f of x concave up, concave down? Where is f prime of x increasing and decreasing? Sketch f prime of x. Careful, that's different than what we've been doing, right? Normally I have you go down a derivative. I'm asking you to sketch up a derivative. Okay, so be careful as you do that. I'm going to give you a few minutes with your neighbors. Okay, go ahead.
Wait, no. There's a chorus.
I know.
Oh, this is next time. I was looking at it, I was like, there is no path. Oh yeah, positive y. So it's the same here.
The positive and the negative.
Oh yeah. The same answer. Same Now we have a sketch that was yeah, so it was like
positive y value is equal to something like this.
Same one that's above versus under.
yeah, that's what we're trying to do. So it's increasing the first half and decreasing the second.
So that means like these functions over x squared, right?
Okay, wait, so at the x-intercepts, it's relative extremities.
So on the prime, where the x-intercepts are, is where the function like increasing.
Pardon the interruption. Can we have Adam Ivan please go to Miss McClure's class? Adam Ivan, Miss McClure's class.
And then right.
And then, yeah, it doesn't change the same level. Does that matter?
The second one, I just wrote above x-axis and below x-axis. Just say
That's illegal.
Or maybe we could just like wherever the answer the other paragraph the reason this is
It's a really social picture. It's actually a really
Any more time? On the pink one. Use your table.
Oh, yeah.
over here, I think, right?
So just where x. Oh.
Yeah. Are we sure it's back? Right. Just switching toward concave.
Yeah, infinity.
So that means you know
Another minute or two.
where is it X? Here, right? Where is it?
I'm not ever going to tell because it's approaching it.
And then the other way is from X is here. Right from the X.
So anywhere.
But like when you look at the like two root graphs, like right here, see it starts going straight up and it's very low.
But we're trying to go from
I was thinking about
Okay, I need a volunteer for the first question. Where does f of x have points of inflection? Okay, Chase, thank you. I need a volunteer for the concave up, concave down intervals.
I can do that one too.
No, thank you though. Concave up, concave down. Intervals, I'm just gonna pick someone. Random number generator. We'll try. Oh, he's about to stand up. I like it. Go ahead. Thank you. Increasing, decreasing f prime. can do that one. Thank you. Okay, the big one. Yes, thank you. I didn't know what to ask. Can you sketch it above where it says 4 types of differentiability so it's in my video?
Yeah, because
What he said.
Yeah, so I was.
It can't be just positive. Why? Oh. But it can't cross the x-axis though. Let's think about all the
I always look at like high school.
That's exactly right.
I think it's increasing as fast as possible. If we can allow time, so it's like at a limited speed. Yeah, because I hate it. I can be functional. Like looking at a function. Like next time, if I go through and they'll talk, go through there, I'll take $1.03.
Okay.
This is so.
Yeah. Okay, let's look. Uh-oh. Uh-oh. All right. Let's look. Okay. So, only one, you guys agree? Only 1 point of inflection?
Yeah.
Yeah, it's okay if you guessed it to be something besides 2. I mean, it doesn't really matter, right? It's just a sketch, but that's the idea. That x-intercept on the second derivative is the only point of inflection on the original, I agree. Okay?
Are we supposed to be like specific? Because I just said like where y equals 0.
Where, yeah, that's fine. I mean, or given a specific thing. I probably should have written numbers in there like I did on the other ones, but this is all sketching anyway because we can't do specifically, so that's fine. Okay, so where is it concave up? Oh, so these ones, positive. Oh, where it's positive. Okay, so let's make sure. I should have done something like this.
Yeah. So less than 2.
Yeah, so this would have been where x is less than what?
2.
No, that's because there's no point at 0.
Yeah, if I do x is less than 2, then that includes 0, which the graph f of x is not concave up at 0. It has an asymptote at 0, right? So I'd say when x is less than 0 or 0 is less than x is less than 2, and then negative would be when x is greater than 2. Or you could have done it in interval notation. I'll do the next one in interval notation. What's the difference between the answers on these two?
They're the same.
They should be the same area, right? Because where my first derivative is increasing, my original is concave up and my second derivative is positive, right? So the only difference I'll do is I'll just write it in interval notation just so you can see the difference, but either one is fine. It doesn't matter which one you do. Okay? Is it correct that the endpoints should be excluded, not included? When I say included, I mean or equal to or square bracket. So is it correct that there's no or equal to and it's a roundy bracket?
Yes.
Okay?
Yes.
So excluded. Yes, because 0 is not a positive or a negative number. It's just 0, right? So it's not increasing, decreasing, concave up, concave down. It's none of those things, okay? Now, let's look at this one, okay? So, there are more than one possibility for this graph, okay? And is it Emily or Carrie? I don't know names very well yet. Carrie? Okay, so Carrie even wrote that here. We don't really know the vertical shift. So do I even know for sure this graph has x-intercepts? What if the x-axis was here, right? We don't know. It's just the basic shape, okay? So here's what I do know. I know that, well, actually, on this one, I do know it has to have an x-intercept. I'll tell you why here in a second, though. Wait a minute. Let me guess here. This is, I want to do it where you had it here. Right? Is that where you had it? Okay. So I know that my second derivative, so this is the second derivative, but it's the first derivative of this one, right? Because I asked you to graph f prime. Does that make sense? Okay, so where this one is increasing and positive, this one should be increasing and concave up, right? Increasing positive, concave up, increasing. So I like up until 0, right? I'm not saying I don't like after 0. I haven't checked that yet. I just like so far. So good. You guys got it? Okay. It had a vertical asymptote, so she chose to give it a vertical tangent line. Great. Okay. Some of you may have chosen to give it a vertical asymptote instead. That would also have been okay, right? We don't have enough information to tell. But if you think about it, doing a vertical asymptote.
Get Igor Kuaku for checkout, please.
No.
She said it right.
Yeah. So if I go here, it's still following all the same rules, right? Positive increasing, concave up increasing. My slope is going to infinity. The slope here is going to infinity, right? It's following all the same rules. There's more than one way to sketch the graph. Does that make sense, you guys? Okay, good. Now, coming here, all right? So this is positive decreasing, right? Positive decreasing means increasing concave down, right? That right here, okay, there had to be a point of inflection, so that must be concave down. I'm trying to figure out where. I think that one's actually like right here. No. Wait for it. Concave up. Concave down. Wait.
That's relative extrema, right? Yeah, it'd be relative extrema.
Oh,
because
yeah. There we go. Okay. So from here to here, increasing concave down. There we go. So there had to have been from here and here a concavity switch of some kind. So if you drew it this way, it would have been something like that, right? Because there had to have been a concave up to concave down switch some way. Good?
Yeah.
Okay. Do you agree that this relative extrema should be a maximum?
Yes.
Yeah, because I'm going from a positive to a negative, which means my one derivative up is going increasing to decreasing. This looks great, okay? So far, okay? Questions? Okay. Then I have this relative extrema around 4-ish or something is this point of inflection here, right? Because the relative extrema, right? Wait for it. Are the points of inflection one derivative up, right? So kind of sometimes it might help you guys if you imagine, if these are only one derivative apart, you can imagine them like that, right? If that helps. Does that help?
Yeah.
See why there had to have been a point of inflection there? Okay, then here, it is increasing the whole time, right? So that has to be concave up the whole time from there till the end. Does that make sense? And then this one is negative the whole time, so it has to also be decreasing the rest of the time. That looks good. Okay? Does that make sense? Okay, so even if you had done it this way, this last part would have to be similar. What? Wait for it. Oh.
There you go.
There you go. So we know that the that first derivative has a horizontal asymptote. We don't know where it is, but we know it has one, right? That's what that's creating. Does that make sense, you guys? Okay. Now, let me ask you this. If I'm trying to think of a way to phrase the question so it makes sense. You guys agreed that the x-intercept, or x-axis, moreover, didn't matter, right? Because it could have a vertical shift, we don't know, right? But would it matter where the x-axis was if I now wanted you to draw the original graph? Yes or no? I'm going to talk about that with your neighbor. Would it matter if my x-axis was brown or green if I now said draw F? Okay, talk with your neighbors. Would it matter if my x-axis was brown or green if I now said draw F?
It's actually it's like x-intercept.
I guess I don't.
Well, you just put the x.
What do you think? If I now want you to draw F, does it matter if I don't know if the x-axis is brown or green? You're saying yes, Sydney. Tell me why. Hold on, listen.
If you're going from F prime to F, the negative y values mean F is decreasing, and positive y values mean it's increasing. So if it was the brown line, F would all be decreasing, but if it was the green line, there'd be part that was increasing and part that was decreasing.
You guys hear what she said? That's totally right. It totally matters. Where the x-intercepts are, we don't know where they are, right? But I can't draw two graphs up, okay? If I could, these things here would have more distinct patterns. But I can't draw two graphs up because if I don't know exactly where the x-intercepts are or if there are any, then how do I know where my graph is going to change from increasing to decreasing? If it was the brown x-axis, she's right. My F graph would be decreasing the entire time. But is that true if it was my green x-axis? No. Right? Because it would have parts that were decreasing, increasing, and decreasing. So it's not that I can't, it's that I don't have enough information right now with where we're at to be able to do that. I can keep sketching derivatives down forever. And eventually they'll all get to 0. Well, only if it's a polynomial, actually. Sometimes in trig and exponential ones, they go in this loop over and over and over again. That's like an oscillating derivative loop, and then I'm like, I'm in the movie Inception, right? Okay, so instead though, I usually get more laughs. Is that not a famous movie anymore? No? I've used that joke for years. Okay, well, thanks a lot, guys. Okay, so, but the idea is that I can draw as many derivatives down as I want, but I can only draw one derivative up because I can take a guess where things are increasing, decreasing, relative extrema are. But once I get to the point where it matters where my x-axis is, how do I know where my graph is supposed to be increasing or decreasing? Does that make sense? I don't know. Okay, what do you got? Questions? Before we do one last thing, we're gonna have bounces today. I'm gonna make Chase through the noise and everything. Go ahead.
I was just gonna say that x-intercepts would also matter because you have to find your extrema.
Exactly, I have to find my extrema. And so if it was the brown x-axis, then I have no extrema. Green x-axis, I've got 2. Well, how do I know, right? Good. Does that make sense? So I can only draw one derivative up, but I can draw as many derivatives down as I need to. Okay, good? Yes, here.
So if you can draw as many derivatives down as you want, how would you notate the derivatives back from just f of x.
So it'd be f prime, f double prime, then the third one is there's 3 tick marks, then 4, and then 5, and then you can start doing like Roman numerals or something like that if you wanted to. Okay? Okay, we got one more thing I want to talk about today, and then we're done. And we're gonna stick together just because it's one of those things that it can be confusing. Did everybody get down? This is my, can I erase it so I have room? Okay, we're gonna talk bounces. Bounces. Okay, Chase, noise? Yeah, that was a good bounce noise. That's good. Okay. Okay. All right. We're gonna do all these things again. We're gonna stick together for time though. Okay. So let's say this is my. We're gonna go here. Okay. Man, this whole multiplicity idea that your teacher probably threw that word in one day for half a second. You didn't realize how much we'd use it in here, huh? Okay. Okay. Hopefully you understood what I was saying by that, right? The multiplicity of the factor here makes it bounce on the x-axis, right? Okay, there we go. So, we're going to stick together for time, okay? We're actually going to answer this question in a second. Well, let's answer it now. If I follow my rule here, okay, where does f have points of inflection? Well, it's where my x-intercepts are on my second derivative, right? Well, how many x-intercepts do I have on my second derivative?
4.
Try again.
Aren't there?
3. No, just 1.
Wait.
Isn't it 6 twice?
Well, the factor occurs twice, but I can't hit it twice and it wouldn't be a function. Okay? Now, let's go in and look at my f of x's. I don't care about this question on this one. Let's go in and talk about where f of x is concave up, concave down, okay? So, at first, f of x is concave up, right? So I'd say from what? Negative infinity.
I think isn't it down at first, the very top, or is that still?
Well, these are positive numbers. So positive y values in my
yeah,
second
yeah.
derivative are concave up. So it's concave up from negative infinity until when?
Negative.
Good. Then negative 3, it's concave down until from negative 3 until when?
2.
Okay. Are we all here today? Oh, okay. Am I going too fast?
It's not that fast.
I'm so fast at writing. You guys should see my circles too. I'm so good at circles on the board.
What the heck?
14 years of teaching right there. You're welcome. 14 years of teaching. Thank you. Thank you. Oh, let's just make sure that the online friends can see the circle, and then we'll go back. Okay. All right. Then what? Concave up, right? From 2 to when? Infinity?
6.
Ah, good. Because at 6, it's not positive, right? And then from 6 to infinity, what is it? There's a problem here. The definition of point of inflection, where the concavity changes. Look, at negative 3, my concavity changes, right? At 2, my concavity changes.
Yeah.
Does my concavity change at 6?
No.
So it cannot create a point of inflection. So what does it create? Well, it's a bounce on f prime.
Would it be like?
Hold on, we're gonna sketch f prime together. I want you guys to sketch f prime, one derivative up. Just try really fast to do it. It's more beneficial, the first derivative up. So you're going one derivative up. It's more beneficial if you try it on your own. Okay? hold on, let me ask you this. If it were going to create a point of inflection on F, then as you're sketching F prime, what should it create? What should 6 create on F prime if it were going to create a point of inflection on F? A relative extrema. Very good. Okay? Right? That follows our row in here. Right? X-intercepts, F double prime, relative extrema, F prime, point of inflection here, right? But something weird is going to happen, and I want you guys to take a couple minutes and try and sketch it. Okay?
It's so funny. It was popular. It's already on my like, there's for sure gonna be
30 more seconds. I know that's fast, I know.
I can see that. So this thing, I think that's the project-wise almost makes sense.
I think it goes like that. Well, I guess, yeah.
But Chase, I want you to go sketch that on the board.
Okay.
No, the original graph can't change.
Do you want me to sketch what I wrote on here?
Oh,
It's okay. What? The original graph can't change concavity, and what can this graph not change? Direction.
Okay.
Increasing versus decreasing. Right?
yeah.
Perfect. It's a horizontal tangent. Ew? What do you mean, ew? It has to go flat without changing if it's increasing or decreasing. Right? Because positive, 0, positive means this has to be, right, positive, increasing, increasing, 0, increasing, right?
Yeah.
Does that make sense?
I see it.
So what's the only way this right here is true? That these x-intercepts create relative extrema on this, creating points of inflection on F. What's the only way that's true about the x-intercept? The thing is the thing. That might be right. What's the only way that row is true, guys? What's the only way that my x-intercepts of my second derivative are going to create relative extrema on my first derivative, creating points of inflection on my original? What's the only way that that's true about the x-intercepts? If there's a change in what? Not concavity. It's a... No, not direction. If it crosses through, if it's a change of the sign, plus or minus sign change, right? So the only way this is true is if it's an x-intercept with a sign change. Crosses, x, axis. The bounce x-intercepts do something different, right? The bounce x-intercepts do something different. They don't create relative extrema on the first derivative. They create horizontal tangents. Because it never crossed through. So positive, 0, positive means this one has to go increasing, 0, increasing. Which would mean my original has to go concave up, 0, concave up. Do I know what that looks like? No, because I can't sketch another graph up. But I know one thing about it, it's not going to be a point of inflection, right? It's not going to be a point of inflection for F. But what is it a point of inflection of? F prime. That's the only way for it to go increasing, 0, increasing. There had to have been a concavity change. So cross through x-intercepts create relative extrema. Bounce x-intercepts create horizontal tangent points of inflection. So much information overload. Okay, we only have like a minute, so all I have time for is to write that out. This is going under this in the same table, okay? This goes under this in the same table.
I gotta rewrite mine.
Yeah, you can rewrite it now. There's always ultralavas over there. Okay, so
It's a summary.
yeah,
Colin made an inappropriate joke.
I know I heard it, but I'm ignoring it for time. This is creating a
That would have been good though. I'll respect that one.
Just take a picture of that and then.
sure.
I'm just not a point.
Okay, here is the last thing. Homework tonight is, I'm not even going to stamp it. You just need to do it. Okay, I assigned that last AP classroom assignment before we had gone through some of this material, right? Because I had assigned it after I had taught it to A2 and then my daughter got sick, yada, yada, yada. So I'm going to reopen it, and those of you, like more than half of you, that were like, well, I did it, I just didn't do the corrections. Well, look, I'm going to reopen it, and now you can do it, okay? So I just want you to look at the AP classroom assignments again, make sure you really understand derivative sketching before we move on. Okay, class Monday is a tough one. Don't miss it if possible, okay? Put on your algebra pants, do your algebra stretches, your lunges, okay, your algebra lunges. Nobody's going to get my joke, it's funny. See, it's good, right? See? Yeah, so algebra lunges, yeah, thank you. Okay, don't miss Monday if possible. If you do, that's fine. But don't miss Monday if possible.
Are we done with this graph now? Can I close down the table? Can I close it up?
I never say close tables. You never know what might come up.
I will add another row spot of it.
If you need to. I think it's done, but I don't know for sure. Hi.
At the bottom of the page, so
Sure.
it doesn't really matter.
You can
We'll just die.
especially the polynomials. Some graphs are kind of weird, but for most graphs, you can jump straight in. To jump more than that, though, is pretty easy. So you wouldn't want to jump more than 2 derivatives.
I thought you just meant like after.